Hello students, welcome back. As I said before, the purpose of lesson 11a is review and summary. Section 2 is mostly review. Rational equations, we went through all these already in chapter 2. Step 1, denominators, step 2, parentheses, and step 3, like terms, and then in the end, you have to solve either linear or quadratic equations, or even higher, but in the end, check for the possible extraneous solutions. That was the idea. Let me go ahead very quickly because we went through every single problems already. So here we go, this kind of problem, and then you can remove the denominator by multiplying the GCD, x minus 1 times x plus 3, to both numerator and denominator. Not both numerator and denominator, both left-hand side and right-hand side to each term. Sorry about that. And then numerator and denominator will cancel each other out. Eventually, we end up with a polynomial equation with no denominator. Break up the parentheses, and then take the like terms together, set them equal to standard form, something equal to 0 form, and factor it, and you're going to get solutions. X equal to -2 and x equal to -3 in this case. But always remember to check for the extraneous solutions. In this case, x equal to -2 will turn out to be okay. Plug it in and check. The detail is left to the students. If you plug in x equal to -3, that's going to be a problem because, as you can see here, plugging x equal to -3, you're going to get 0 in denominator. So that's not a solution. Only x equals to -2 is a solution. So x equal to -2 is the only solution here. You can check it with Mathematica like this. We went through this very quickly here because this is a review. Actually, this is review of review. We went through this already in intermediate algebra, and then reviewing again. Okay. Radical equations. Okay, this too is a review, but it's long and tedious. So for example, what if you have just one radical? Isolate, take the square of both sides, and then go from there. Remember to check for the extraneous solution. This square root is already in isolated form, so square both sides. The right-hand side is complete square, so we get something, and then eventually that becomes a quadratic equation. Be sure to check for the extraneous solution. No, this one is yes, so we have only one solution. What if we have two square roots? In that case, we have to isolate one and square both sides to remove one square root, and then the other square root will stay. And you have to do it again. Isolate and take square both sides. Now you can remove both square root. Kind of like this. First square root is already isolated, so square both sides. If you take the complete square of the right-hand side, we get this part. So square root does not go away. So isolate this one, flip it over and isolate this one like this in the right-hand side, and square both sides. Finally, we end up with a quadratic equation like this. You can set up and solve, and you get two possible solutions. And make sure you test both of them into the original equation and check for extraneous solutions. Maybe one, maybe both, or maybe 0 solutions. In this case, x equals to 0 is not a solution, it's extraneous. And x equals to 8 turns out to be a solution, so we have only one solution. But all three is possible. Both are solutions, neither is solution, only one of them is solution. So check for extraneous solutions. Okay, so much for equations. Now let's talk about inequalities. These kind of inequalities, well, let's see. If you have just one rational function and less than 0, greater than 0, we went through those in previous lesson, in lesson 10. But here, we have some complicated rational expressions. What do we do? Similar thing here, we have complicated rational expressions. What do we do? And these kind of things, of course, these are going to be new to everybody. Okay, one at a time. In this case, it's better to move everything to one side and then consider less than 0 or greater than 0, and then take the common denominator and get big rational expression. Okay, here we go. No, this one first. Flip everything to the left-hand side, and then less than 0. Now take all these together by taking common denominator. Work out, and we end up with a rational equation. Rational inequality, excuse me. How do we handle rational inequality? We did it in the previous lesson, lesson 10. Factor, and then we get that. And then what do we have? We have 4 factors here, 2 from the numerator, 2 from the denominator. So 2 zeros and 2 poles. And then these 4 numbers divide the number line in 5 pieces. And then using the multiplicities, you can check which one is part of the solution and which one is not part of the solution. In short, we end up with this kind of diagram. So negative 3 and positive 3 halves, those are zeros. And negative 1 and positive 1, those are poles. And then they all have multiplicity 1. So sign change everywhere. And then right hand side here, everything is positive. X is humongous, so everything is positive, but we have the extra negative sign there, so we begin from negative. And sign change, sign change, sign change, sign change. And then we simply take what? Negative intervals. We want this thing to be less than 0, so negative interval. So here, less than negative 3. Here, between negative 1 and positive 1. Here, greater than 3 halves. In the interval expression, well, never mind by interval expression, you can do it on your own. That's one way to handle it. But then again, this is a very cumbersome job. And also, in the end, everything boils down to this diagram here. And it comes from, where do we get all these numbers? We get all those from equations. So one way to handle it is to do this. I mean, previous method is legitimate method, same method that we used in the previous lesson, lesson 10. But here's another method. Because of that method, all you have to do is to find out those crossing values, poles and zeros. So forget about the inequality and simply solve an equation. Okay, solve it, and then we got this. All right, those are the zeros. And then when we have denominator equal to 0, we have two denominators, x equals to x minus 1, x plus 1. So x equals 1, x equals to negative 1. So we have 2 zeros and 2 poles. And then same diagram applies. This method is a bit of a cheating because it depends upon the fact that previous method is valid, but it makes our life simpler. So you can forget about the inequalities, forget it completely, and then solve the equation, and then hit vertical asymptote separately, and then you can do the sign analysis. Here's another problem here. This time, let's do only the first solution. That is, forget about the inequality, just solve an equation. Use the same method, denominators, parentheses, like terms, and then we get solutions. Okay, we got those, all right, 2 zeros. Now let's find poles. Look at the denominator separately. X equal to 0, x equal to 2. Those two. So we have zeros, and then we have poles. X equal to 2, x equal to 2. Wait a minute, they're common. So we have only 0 to 7 to work with. So 0 to 7 to work with. And then we have to do appropriate sign analysis. Because they're common there, so the multiplicity is 0, so we don't have sign change, but that's a little bit difficult to understand. So for this kind of method, we simply select a number and then plug those in. Select any number between 0 and 1, 0 and 2, like 1. Select any number between 2 and 7, like 5, and select a number and plug in, select a number and plug in, and you can work like that. Okay, it's a little bit more cumbersome than the multiplicity method, but it works anyway. Let's move on. How about radical equation? Similar. Forget about inequality and solve an equation, and then set all those in number line and then do the sign analysis. Okay. Forget about inequality and solve an equation, excuse me. Work out, all right. And then we get that. Consequently, we get that. And then one is extraneous and the other one is legitimate. So we have x equals to 8. Okay. All right. So this x equal to 8 is going to divide the number line in two pieces. But you see, before the number lines, there are two radicals. This must be valid and that too must be valid. So you have to consider those. So 2x is greater than or equal to 0. X plus 1 is greater than or equal to 0. Put those together, you get x is greater than or equal to 0 only. So from here, I can divide by 8. From 0 to 8, 8 to infinity, we have t is 2. And then plug a number, say 1 here, and plug it in and do your computation. And plug a number in, say 9, and plug a number and then do your computation. And then you're going to get appropriate inequality. And this is the one you're looking for, so the answer is 0 to 8. You can cross-check with graph. Okay, let's race through. Final problem here. Again, similar fashion. Forget about inequalities and just solve an equation. And then we got everything done, all right. So we have x equal to 4, the solution, okay. And then we have to remember the square root expression must be valid. So this has to be greater than or equal to 0. So x has to be greater than or equal to -1/2. So from here, I have to get x equal to 4, which will divide this half number line in two pieces. So -1/2 to infinity. 4 is here, and then you can plug a number in, and which is which. Plug in, say, for example, x equal to 1 here, x equal to 5 here, and work out. We have this and that like this, and select appropriate interval. Turns out this is the right one, so there goes your answer. And here's the graphical justification. You see, as you can see here, the function is greater than 0. Okay, so much for radical inequalities. That completes it.